well, first to start off, my thesis is on task planning for Earth observing satellite systems. And this image in the backdrop of the slide is actually one of the early spotlight images from the radar imaging satellite that I work on here at Capella Sequoia that was actually captured last week using some of the task planning methods developed and based on some of the research and things that I've learned here. So Earth observing satellites, as well as the information they provide, are relied upon for essential information by our governments, researchers, as well as commercial industries. And all of them have come to depend on them for various applications that affect all of our daily lives. Common applications include infrastructure mapping. If you've ever wondered how Google Maps knows when new buildings appear or when new roadways are constructed, they generally do this by analyzing large swaths of satellite imagery data. Another common application is human activity monitoring. We live in a changing planet and people want to know what other humans are doing. Types of human activity monitoring applications include watching for illegal deforestation in the Amazon, monitoring for illegal fishing, or one application you can see here is you can detect evidence of planes taking off at Travis Air Force Base, just north of us here in San Francisco, from changes in the surface roughness at the dirt at the end of the tarmac. Another historic application is object detection and classification. Historically used by military and defense and intelligence organizations, object detection and classification allows you to understand the type, the asset, and the disposition of various forces or various objects at remote or otherwise inaccessible locations, intelligence that can be hard to come by or outright impossible to come by other land-based metrology systems. And additionally, an emerging application is economic analysis. This can be as simple as counting the number of cars in a parking lot, the amount of shipping containers in a port, the amount of oil in an oil well, and it's used by financial analysts, traders, as well as governments to understand the flow of productivity and commerce in an increasingly globalized society. Before jumping into the satellite task planning problem, a little bit of a history lesson on Earth observation satellites, as well as their history, is in order to provide some context for the state of the art. Space mission operations, as well as satellite task planning, developed to support high-value single asset missions like the Keyhole 9 satellite shown here below. After the launch of Explorer 6 in 1959, both the United States and the Soviet Union realized the value of having space-based remote sensing systems and initiated long-running intelligence gathering programs based on satellite platforms. These early programs heavily influenced both the development of space operations as well as satellite task planning as a whole. Early remote sensing satellites relied on physical film that had to be returned to Earth in re-entry capsules. You can actually see the 4 re-entry capsules of Keyhole 9 on the left, as well as one of the rare photographs of a capsule being jettisoned and being captured by plane for later processing on the right. Because of needing to carry both the film, the re-entry capsules, as well as the cameras on board, these satellites were massive in size, approximately 23,000 pounds, and because they would run out of film relatively quickly, operated only for short durations, only about 124 days on average, but as little as 30 days at times. And so because of the criticality of these missions, the planning process for every single Keyhole satellite launched was an incredibly orchestrated affair. All of the imaging targets would be selected months in advance and planned out by human operators, as well as the on-orbit operations being closely orchestrated to deliver tightly controlled outcomes. There simply wasn't a need for more complex automated mission operations or mission planning. However, that's changing in the modern era. Innovations in the launch industry, including reusable rocketry, which is lowering the cost and easing access to space, as well as the demonstration of small satellites as cost-effective remote sensing systems, has led to a rise of a new generation of small Earth-observing constellations. A constellation being multiple satellites operated in coordination with one another to improve the overall throughput or responsiveness of the data collection capabilities. In the plot below, you can see the total number of Earth observation satellites launched from the very first one of Explorer 9 through the modern day, with this plot generated being about 2 weeks ago, so it's a little out of date. However, more Earth observation satellites have been launched in the last 6 years than in the preceding 30. There's a huge new wave of constellations being operated, and human operators are quickly being outpaced by their satellite charges. This means that the new constellations require highly automated mission operations to meet their stated throughput and responsiveness objectives. Automating all of mission operations is a task well beyond the scope of my own thesis. However, having automated and efficient satellite task planning algorithms is a key component of that. That component is what my thesis focuses on here. So what is the satellite task planning problem? Given a constellation of satellites and a time horizon, what should those satellites do? What locations should be imaged? When should those collections be taken? The sample data set that I consider in most of this work is the 1,000 most populated cities as taken from Simple Maps' World Cities databases. People generally want to know what other people are doing, so we find this as a representative data set for imaging locations. The satellite task planning problem is equivalent to the time-constrained task selection problem, which is an NP-complete problem, meaning that there's no known polynomial time solution algorithm for it. This means that as the number of requests and requested imaging locations increases, as it will with new constellations with more imaging capability, it's going to be more and more challenging to solve the satellite task planning problem. Therefore, we need to try and find application-specific solution methods that are going to be able to scale with these new constellation sizes. As a step towards autonomous mission operations and efficient satellite task planning, my research addresses the following questions. The first question is, can we analyze the satellite task planning problem to determine effective solution approaches? This led to the development of a unified modeling framework for the satellite task planning problem. The second contribution tries to solve how can we efficiently task large constellations of spacecraft. This led to the development of a maximum independent set approach for satellite collection planning. And the final question my research seeks to address is how can we account for satellite resource constraints during the planning process? This led to the development of a Markov decision process formulation of the satellite task planning problem. And without further ado, we'll get started with the first contribution, the unified modeling framework for studying the task planning problem. I'm not the first person to study satellite task planning. In 2008, Bianchessi developed a heuristic selection algorithm and applied it to the 4-satellite Cosmos SkyMed constellation of radar imaging satellites. In this approach, he would time sort the order of collection and data downlink opportunities and simply select them in time sorted order if the next upcoming opportunity was feasible. Otherwise, he would discard it. A more recent contribution is the graph traversal method developed by Augenstein for the SkySat-1 Earth imaging satellite. In the Augenstein's approach, collection opportunities are modeled as nodes in a graph, and feasible transitions are represented by edges. The optimal schedule then is simply the longest weighted path through the graph. In 2016, Augenstein developed a mixed integer linear programming formulation of the satellite task planning problem, where collections are represented as binary decision variables, and the objective is to maximize the weighted sum of all collections taken. A set of linear constraints are applied to model mutual exclusivity between different collects so that collects that would be incompatible with one another are not allowed. Now, one of the challenges in understanding the fundamentals of the satellite task planning problem is all of these solution approaches have slightly different modeling objects at the core of them, making it hard to really understand what the core of the problem is and what we can do to solve the problem more efficiently. So one of my contributions is making the problem a little bit worse and coming up with a new modeling approach for the problem and to try and gain some insight into the fundamentals of understanding the task planning problem. This modeling approach is developed as follows. First, given an input set of requests R, each with some reward weight W sub R. The request can be an area, as shown on the right, or a single point. Each request is then decomposed into a set of tiles. This decomposition is based on the satellite orbits and also depends on the exact payload sensor the satellite is flying. Different optical sensors will have different fields of view, as well as different radar satellites will have different beam widths. This decomposition allows a guarantee of having the entire requested area covered by collects. Finally, for every single tile, we use the satellite orbits again to compute the collection opportunities. These collects are discrete times where the satellite would be able to take an image. The collects, denoted by the set X, each have a start time TS and an end time TE. For every single tile, there may be one, multiple, or even no collects over the course of the planning horizon. One advantage of this modeling approach is that it's highly parallelizable. Both the tessellation step as well as the collection search step can be done in parallel. Therefore, as the number of requests grow with the planning problem, we're able to keep up with computing the action space, that is the collects, by throwing more cores or more processors at the machine. Now, so far, I've only talked about half the problem, the collects themselves. The other half of the problem is the decision part of the problem. Why can some collects be included in the schedule and why can some collects cannot be? Therefore, we consider a family of constraint functions K that take in 2 collects and map it to an indicator variable 0 or 1. These indicator variables essentially convey whether both collects can be included in the schedule by a 1 or they cannot be included in the schedule by a 0. Common constraint functions include agility constraints, Agility is a common problem for small, agile Earth-observing satellites, where at the end of one collect, they have to slew to reorient before they're able to capture the next collection opportunity. The attitude at the end of the collect must be reoriented to the new attitude using the onboard attitude determination and control system. Now, we use a simple linear slew model based off of the starting quaternion attitude and the ending quaternion attitude plus some settling time. However, if a more complex attitude model is desired, this agility function can be swapped out for a full simulation of the attitude determination and control system on board the satellite. The agility constraint is then simply returning a 1 if the computed slew time between the two orientations between any two collects is less than the time between the end of one collect and the start of the next collect. The other common constraint is the repetition constraint. The repetition constraint encodes the desirement that you don't want to collect the same tile or satisfy the same request multiple times. Therefore, a repetition constraint returns 1 if the requests generating each of the two collects are different and is 0 otherwise. This is essentially just saying you don't want to image the same thing multiple times because you only get the reward for it once. With these constraints, as well as the modeling fundamentals, the task scheduling problem then becomes finding a scheduled subset XS that is a subset of all collects such that the schedule objective O of X obtains a maximum at O of XS. Another way of saying it is you want to maximize the total number of scheduled collects in the planning horizon. Necessary but not sufficient conditions for optimality are that for any pairs of collects in the scheduled subset XS, all of the constraint functions evaluate to 1. This is an intuitive property because otherwise, if any two constraints in the scheduled subset evaluated to 0, that would mean there'd be some infeasible transition occurring in the schedule. And ultimately, if any infeasible transition is in the schedule, it's not going to be realizable on actual satellite hardware. So the schedule is no longer optimal and no longer able to be executed. The objective is to simply maximize the total reward of all collects. Now, given these modeling fundamentals and constraints, there are two interpretations of the problem. The first is a feasibility interpretation. Here, collects are represented as nodes in a graph, as done with Augenstein, and feasible transitions represent edges. The infeasibility interpretation is a new interpretation of the problem where collects are also represented by nodes in a graph. However, the edges now represent mutual incompatibility. That is, if two nodes have a common edge, it means that they cannot be taken or included together in a single schedule. One thing to note is that the feasibility interpretation has many edges in it, whereas the infeasibility interpretation appears relatively sparse. This is also a somewhat intuitive property if you think about it, because if you consider a 24-hour planning horizon, a collect at minute 5 of the planning horizon isn't going to affect what the satellite can do at hour 23 of the planning horizon. So that's a possible transition that's able to be made, even if it's an incredibly useless one to make because you want to be making collects in that intervening time. It is still part of the possible action space of the problem, which is a property that will crop up later. Another interesting property of the feasibility interpretation is that it cannot capture multi-satellite interactions without admitting contradictions. If we consider this example problem here, with 2 satellites denoted by blue and red respectively, and 4 collects numbered 1, 2, 3, and 4. We can have transitions between different satellites because intuitively nothing that satellite 1 does should affect what satellite 2 is able to do from an agility perspective. So we have edges between 1 and 3 and 4. One possible feasible schedule is transitioning from 2 to 3 to 4. Another possible schedule, if we follow the edges of the graph, is transitioning from 1 to 3 to 4. However, this admits a contradiction because there's no edge between vertices 1 and 4. That isn't an admitted solution. So by allowing interactions between disparate satellites, the feasibility interpretation, at least as it's set up naively, cannot capture these multi-agent interactions. And therefore, the satellites must be solved separately when using a feasibility-based approach. What does this look like for a real satellite task planning problem? If we consider a scenario with 2 spacecraft, 100 requests, and 287 collects, these are the resulting feasibility and infeasibility interpretation graphs. The feasibility interpretation graphs look a little COVID-y or like a pepperoni pizza, if you will. Again, this is because they're an incredibly dense representation. All of these are edges between vertices in the graph. I couldn't find a better way to plot this just because of how many edges are included in the interpretation. There are ultimately 20,000 edges, over 20,000 edges for the feasibility interpretation. The infeasibility interpretation, on the other hand, is a relatively sparse interpretation of the problem. For the same representation and problem, there are only 687 edges, and you can see that there are many disconnected subgraphs. This informs us that the problem is generally going to be largely separable, and the infeasibility representation is also a more compact or informationally more efficient way of representing the problem. Really, it's only storing the essential information on needing to make decisions in terms of contradictions. What happens when we also look at it for larger problems? Well, this trend continues to hold up as we grow the number of requests. So if we consider a one satellite scheduling problem and requests varying from 100 to 15,000 and nodes varying from 138 to 21,000. For the feasibility interpretation, that graph has over 20 million nodes and an edge density of 96%. For the infeasibility interpretation, they're the same number of nodes or vertices in the graph, but only a little under 10 million edges, leading to an edge density of just under 4%, a much more compact or sparse representation of the problem, showing that we're likely going to want to work on infeasibility interpretations of the problem if we want to find efficient methods for satellite task planning. So if we try and classify existing methods that have been applied to the satellite task planning problem, where do they fall in each interpretation? Well, random selection, heuristic methods, as well as graph search, and in addition, the Markov decision process formulation I'll discuss later fall under the feasibility interpretation. In the infeasibility interpretation, that would be the mixed integer linear programming or maximum independent set method we'll shortly introduce. So wrapping up, the analysis has shown that we want to work on infeasibility interpretations of the problem. So then knowing this information, how can we answer the question of how do we want to task large constellations of spacecraft? This leads to a maximum independent set approach for satellite task planning. The idea is relatively simple. When request weights are equal, that is, all of the request weights are equal to 1, the scheduling objective simply becomes O of x is equal to the cardinality of the subset xs. That is, you want to maximize the total number of scheduled collects in the scheduled subset. This means that an optimal schedule is simply the largest subset of the infeasibility graph with no common edges. We can still see that same example problem for the feasibility incompatibility in multi-satellite problems, just reinterpreted in the infeasibility view. We can see the same 4 nodes and now a single edge representing the incompatibility between the 2 blue nodes. There are 2 maximal independent set solutions to the problem where either of the 2 blue nodes is selected and both of the red nodes are included because they are free and there's no edge between them in the problem. This is important to note that there may be multiple optimal maximal independent set solutions that are all of equivalent quality. So if we want to try and solve the satellite task planning problem as a maximum independent set problem, an important thing to note is that it is also NP complete. Therefore, we also need to find heuristic solution algorithms for satellite task planning. Thankfully, there have been a number of advances in graph theory in recent years for solving the maximum independent set problem at scale. In particular, one incredibly effective algorithm is the local search algorithm developed by Andrade et al. That takes existing subset of graph vertices X and looks to improve the number of vertices included by removing and adding nodes. The algorithm can be described simply as thus. It works in terms of improvements, which is trying to take an existing subset of nodes and adds more to it. A 1 improvement is removing 0 nodes and simply adding 1 node into the graph. This applies to any free nodes. A 2 improvement looks to remove 1 node and add 2 nodes into a candidate independent set. A 3 improvement consequently follows the same pattern of removing 2 nodes and then adding 3. This type of improvement or swap can be generalized up to any n-level improvement where you remove n nodes and try and add n+1. However, there are efficient linear time solutions that are known for 1 and 2 improvements. So we can apply a 2 improvement based method to the satellite task planning problem and compare it to what can be found using a mixed integer linear programming approach. So the mixed integer linear programming approach is called the global solution. It's allowed to run to completion to find the truly maximal independent set and compared with a 2 improvement based method for requests numbering 100 to 5,000. We can see for a few numbers of requests, the 2 improvement does generally well and finds the same global optimum as the mixed integer linear programming approach. However, as the number of requests scales, there's this gap between the 2 improvement based method and the global optimum. Ideally, we aren't going to have that gap. You want the maximum independent set method to be able to find as good solutions as the mixed integer linear programming approach at scale. So what can we do? Well, we can apply graph kernelization techniques along with local search and evolutionary algorithms to find maximal or near maximal independent sets at scale, and these techniques work incredibly well for sparse problems. One evolutionary approach that we apply to try and find large independent sets is the Evomis algorithm. Here we consider two parent populations denoted by the horizontal stripes and the vertical stripes on the left. These are two candidate independent sets. We then try to evolve these two parents by selecting three different subsets of nodes in the graph, V1, V2, and Vs. V1 and V2 represent the parts of the gene, or, well, the candidate independent sets that we're going to combine to make a new child, and Vs is a separator set that guarantees that the independence of the child, that it is still an independent set, is preserved during the recombination step. So what that looks like is we take V1 from the first parent, V2 from the second parent, and combine them into a new independent set. And then we can apply the local search algorithm of Andrade et al. To fill in any remaining gaps to get an even larger independent set. What happens when we apply this to solve real satellite task planning problems? Well, first we want to study a non-constellation problem with simply one satellite. Here we consider a maximum independent set method, a maximum independent set method with a 10-second timeout, a MILP-based solution, and a graph solution. On the left, you can see the number of scheduled collects, and on the right, you can see the runtime for each solution. One thing that we can see is that both the maximum independent set, the maximum independent set with a 10-second timeout, as well as the MILP solution, all find the globally optimal outcome. However, if we look at in terms of runtime, something interesting appears. Both the graph and the MILP algorithms start to take significantly longer to arrive at that global optimum compared to the MIST solution, especially for large problem sizes. This is believed to be because the graph has a harder time of acting at scale, and the mixed integer linear programming approach has a hard time running the simplex method to iterate through all of the possible integer constraints of the problem. What happens when we look at a more real-world problem? We consider scheduling the SkySat constellation. The SkySat constellation is a constellation of 21 Earth imaging satellites currently in operation today. We consider scheduling requests from 1 to 10,000 for the problem. Again, we can see that the maximum independent set methods perform incredibly well. However, something interesting begins to appear. They appear to outperform the mixed integer linear programming solution, especially for very large solutions. One thing to note is for all of these simulations, we apply a 15-minute timeout to all of the solvers, so they actually return a solution before the end of the universe, and I can actually complete these runs. And so at the 15-minute mark, we send a termination signal to the solver and let it take however long it takes to complete and return its solution at that time, and that is what it provides. So as the size of the problem scales, we send the same termination signal at the 15-minute mark. However, it takes a very long time for the MILP solution to return at that point. Additionally, the solution that it is found by that time is not as good as either of the maximum independent set approaches. Another interesting thing to note is that the maximum independent set approach reaches a plateau relatively early on, even though it is returning a solution just as good as the maximum independent set with a 10-second timeout. This is indicative of the heuristic algorithm spending a long time trying to recurse on the problem to try and find better outcomes, but being unable to do so. It doesn't have a good stopping criteria, though it does find a large independent set relatively quickly. What happens when we apply this to a problem larger than any that exists today? So we consider scheduling a 24 satellite constellation. We see a very similar trend emerge, and the trend actually still hold. The maximum independent set solutions outperform the MILP and the graph solutions. There's a slight uptick in terms of the runtime for the MIST solution as the problem size scales, even with a 10-second timeout, but it's significantly less than the mixed integer linear programming solution. In both cases, the maximum independent set approach far outperforms the MILP solution in number of collects as well as runtime. We can also look at in terms of a bar graph, which is a slightly easier way to understand the efficiency of the maximum independent set solution. On the left, we can look at the absolute performance of the 4 solution methods for the 10,000 request problem. The maximum independent set performs the best. The maximum independent set with a 10-second timeout performs the next best, and the MILP slightly less than that. The graph solution generally performs poorly because it isn't able to recurse through the large amount of the decision space by the time that the stop to the solve is called. However, once we start looking at the normalized performance of the solvers, an interesting trend appears. If we normalize the total number of scheduled collects by the amount of runtime that the solver takes, we see that the maximum independent set solution with a 10-second timeout is actually the most efficient. It's scheduling a little less than 9 collects for every second of computational runtime. The MIS approach is now the next most efficient, scheduling a little under 5 collects for every second of runtime, while the MILP and graph approaches are only scheduling about 1 collect for every second of runtime that they were allotted. This indicates that the maximum independent set solution is an incredibly efficient method for scheduling the satellite tasking problem at scale. Additionally, it shows that there's an area of future improvement by selecting a proper stoppage criteria for the maximum independent set solution so it can terminate efficiently once it has found what a near optimal or truly optimal maximum independent set. So with that, we've found a way to efficiently schedule satellite constellations at scale. One thing that we haven't considered, however, is how do we account for resource constraints during task planning? The last part of my research focuses on developing a Markov decision process framework for solving the satellite task planning problem with resource constraints. Why do we want to consider satellite resource constraints? Well, for small satellites, the reduction in size frequently necessitates compromises in system design. A Keyhole 9 weighs approximately 12,000 kilograms, whereas a SkySat weighs only about 120. With the reduction in size come compromises in system design and challenges in the amount of space that you have to put in new parts. Possible resource constraints include data storage, data downlink rate, energy storage, power generation rate. If you have a smaller satellite, you have smaller solar panels. The amount of thermal capacitance or thermal dissipation, as well as the bus power usage, payload power usage, or propellant mass are all things that we might want to consider during the task planning problem. What happens if it isn't considered? Well, if we solve a satellite scheduling problem using a MILP method without accounting for resource constraints, we can see the power reserves on the left and the onboard data on the right. Without considering power constraints, we see periods where the power drops below 0. We've successfully planned our satellite into the ground, a really awkward thing that you never really want to have to tell your boss that you forgot to include power constraints in the problem and you commanded your freshly launched satellite into the dirt. Similarly, for onboard data constraints, you can see if they're not accounted for, it's possible to schedule more collections than what is able to be stored on board, meaning this data would be lost. It wouldn't be able to be recorded and therefore, for all intents and purposes, is relatively useless. So how do we account for these constraints during satellite task planning? Well, thankfully, we have Markov decision processes. Markov decision processes are a generalized decision framework that are able to incorporate complex system models in the decision-making process. They're formulated in terms of state, action, transition, and reward, and can be graphically represented like this on the left. The way it generally works is that at a given time or a given state, the agent takes an action A0 and receives a reward R0, and then it advances probabilistically or deterministically in this case to the next state. So how do we pose the task planning problem as a Markov decision process? Well, first we need a state space. We define the agent state space in terms of the current time, the last collection or ground contact, the set of requests that have been imaged by a given time. This allows us to encode repetition constraints in the problem. And then finally, we add in 2 variables, D and P, to represent the current onboard spacecraft data and onboard spacecraft power. Next, the action space is as follows. The action space is selecting a start time for the next action, the end time for the next action, as well as the action type. The action type can be either a collection, a data downlink to a ground station, or a nil action. The nil action is important to introduce because it allows the spacecraft to not use power resources that are required during a collect or a downlink and otherwise recharge during the period. This allows us to find actually feasible solutions. Finally, the state action transition function. This allows us, after selecting a given action, to advance the state properly to the next state update time. The way we do this is given the time of the next action, that simply becomes the time of the agent at the next state iteration. Similarly, if the action is a collect or a data downlink, we advance the time of the previous action that is included in the state space. This is necessary to apply agility constraints properly because you need to know the time of the last orientation of the spacecraft to properly encode whether it's feasible to reach the next orientation. Similarly, we update the record of all collects that have been taken on board at that time if the action taken is a collect and it's within the bounds of the onboard power and onboard data constraints. If it's not, we actually don't update that we have taken that collect because we wouldn't have been able to successfully do it. Finally, we include simple linear power and data models. Now, these models are relatively basic, but they allow us to propagate the amount of power usage through a collect or through a data downlink. And theoretically, we could exchange these for a more complex system model or a black box model based on the system engineering of the problem. And finally, for the reward space. The main property of the reward space is you receive a reward if you take a collect. The one important variation is we need a penalization term here at the front of the reward that discounts collects taken further out in time. This encodes the idea that it's better to take actions earlier in time. Otherwise, for the planning agent, it would look as if a collect taken at the 23rd hour of a planning horizon is the same as a collect taken at the first hour of a planning horizon. And really, you want to try and do as many things as early in time to use up your resources as you have them. Similarly, we provide small rewards for doing a data downlink or taking a nil action because you don't want to penalize the satellite for doing nothing, if that is the only safe thing it can do. Similarly, we apply stiff penalties for running out of power or running out of data. Now, if you implement all this, you'll still be waiting around forever for a solution. And why is that? Well, the request collection history IC induces a state space size of 2 to the R. So for a problem with 300 requests, a lower bound on the state space size is 2 to the 300, about 10 to the 90 or more atoms than exist in the known universe. So you're gonna have a hard time finding a computer that can solve that problem. So what can we do? Well, we can move from exact solution methods to online search methods. So move from value iteration and policy iteration to depth first search and Monte Carlo tree search. We can also move from interpreted code to optimized compile code to decrease the runtime of the search action. Finally, we can move from a Markov decision process variation to a semi-Markov decision process variation. So what are the online solution methods that we're going to apply? The first is depth first search. This is a relatively straightforward search method where you start from an initial state and fully enumerate all different states and actions down to some depth and breadth and count the reward for being in any of the child states down the tree. Once you have fully enumerated the tree to your desired depth and breadth, you propagate back the state rewards up through the tree to the root state, and then simply select the optimal action at that time. This is relatively straightforward to select. However, it spends a lot of time enumerating states that are known to be poor states. It has to fully enumerate every single action in the tree to your fixed depth and breadth. A better solution method is Monte Carlo tree search that uses random sampling to efficiently balance exploration and exploitation throughout a decision tree and has been used in problems like AlphaGo to efficiently explore incredibly large state spaces. A brief summary of how it works is as follows. Based on some existing tree, you then select a child node and then select one following action and begin a rollout of different states based on some existing policy. For the satellite task planning problem, we honestly can just use a random selection policy, though the problem could be optimized further by tuning the selection policy of that random rollout. All of the states and rewards visited by the random rollout are cached by the solver and propagated back up to the root state. And the problem continues randomly sampling different actions as part of the tree and remembering the outcome. At the end, where there's some stoppage criteria, the algorithm looks for what the optimal action is and selects it and advances to the next state. Then the process repeats itself until the end of the planning horizon is reached. So even if you do all this, you still won't actually find a solution in time. A Markov decision process evaluates the problem at a fixed time step, and this ultimately becomes a challenge for the size of the horizons that we're trying to consider here. Because collection opportunities occur at very precise times, you can predict them down to the millisecond actually, you need a fairly fine time discretization of the Markov decision process to fully capture all of the different collection opportunities. For a 1-day planning horizon and a 1-second time step, that ends up being 86,400 evaluations of the decision policy. A very large computational effort. However, we can leverage our knowledge of the satellite task planning problem to make the problem more efficient. We know a priori the exact times decisions have to be made. Realistically, after taking some collect, you don't need to redecide every single second what you're going to do until the next collect. You just know this is the next collection I'm going to take. This leads to a semi-Markov variation of the problem where we no longer have a fixed time step for evaluation and instead have variable time steps between policy evaluations, where the decision policy is evaluated only at the times where collects or data downlinks occur. For a 1-day planning horizon with 1,000 requests, there are only approximately 3,000 decisions that would need to be made, a 28-time reduction in the size of the decision space or the number of decisions that need to be made. This is enough of an improvement to be able to get the Markov decision process formulation into the realm of being computationally tractable. So what does this look like for a real problem? We can see on the left the evolution of the depth-first search algorithm, and on the right, the evolution of the Monte Carlo tree search algorithm for a problem with about 500 requests. One interesting thing to note is the depth first, well, you can see the power on the top and the data usage by the satellite on the bottom. One interesting thing to note is the depth-first search generally stays at the lower bound of the power level, whereas the Monte Carlo tree search method generally balances more evenly throughout the entire power regime. The reason for this being is the Monte Carlo tree search algorithm is generally less myopic than the depth first search algorithm. It is able to see farther in time by spending its computational resources evaluating long decision paths, whereas the depth first search is fixed, spending its decision resources constantly reevaluating what's immediately in front of it, and it isn't really able to see trades that exist out in the horizon. The nice thing to note is both algorithms are very safely able to stay within the bounds of power and data constraints, which is the ultimate objective of this planning solution. Though there's clear room for improvement by tuning the Monte Carlo tree search or depth first search algorithm to better try and trade where we stay in the power regime or stay within the data regime. Ideally, we'd never be getting to points like this on the bottom where the data is totally maxed out and we're unable to take any more collects. So that brings me to the conclusion of my thesis defense. In summary, my research has yielded the following contributions. First, we've developed a modeling framework for the space mission planning problem. This has developed a unified modeling framework that's able to handle both point and area collects, as well as a fast parallelized algorithm for computing the action space by decomposing it into tiles as well as collects, all of which can be shipped off to separate machines. Additionally, we've stepped through an analysis of the feasibility and infeasibility interpretations of the satellite task planning problem and gained some insight into the underlying structure of it. The next contribution of my research was maximum independence set planning. We identified the maximum independence set problem as having a direct correspondence and application to space mission planning and showed how experimental methods in graph theory can be used to efficiently plan large constellations of satellites. Finally, we introduced a Markov decision process formulation of the satellite task planning problem that was able to incorporate power and data constraints into the planning problem and compared two different solution methods for it. During the course of my research, it has resulted in a number of publications. The research shown here has largely been published in the two publications highlighted in black, published in IEEE Aerospace and the Journal of Spacecraft and Rockets. I actually somewhat stupidly looked at the reviewer response today for the Journal of Spacecraft and Rockets this morning, but very thankfully, the paper was just accepted as of this morning, which is incredibly exciting news. Also, I should have told you that, Michael, a little bit earlier than this. Additionally, in the course of my research, I've been able to publish and also maintain a number of open source packages for astrodynamics, as well as satellite task planning, written in Julia, Python, as well as more recently Rust. You might be able to see a slightly sick trend in wanting to rewrite astrodynamics every single time a new language comes out, but I do find it a very good way to pick up new programming languages. One of the more exciting things is these libraries have been used by a number of commercial companies, including people at Blue Canyon, at Astranis, at the National Observatory in Brazil, that is what the big O is, as well as Zona Space Systems, in developing their satellites as well as their systems.